One of the prime purposes of algebra is to represent patterns in a nice, concise, simple way without a lot of words. Here's an example of what I mean. We have a set of diagrams here made up of triangles. Diagram 1 is made up of one triangle, diagram 2 of two triangles, and so on. And what we're being asked to do here is to find the number of segments or sides needed to produce each figure. In other words, we're looking for a relationship between the number of polygons, triangles in this case, and the number of sides or segments needed to make that figure. Alright, so just to talk about this, I'm going to call the number of polygons, I'm going to assign it a variable, n, and the number of sides, s. And s is what we call the dependent variable in this situation. N is the independent variable. And what that means is that the number of sides depends on the number of polygons, not the other way around. Alright, so we're going to look for a pattern between these two quantities, and a good way to try and figure out patterns is to set it up in a table. So I'm going to put my independent variable here, n, and my dependent there, and then I'm just going to go through each diagram and count the number of sides. So in diagram 1 I have 3 sides. It's kind of like my starting amount. Diagram 2, I have the 3 from before plus 2 more. So that's 5. And in diagram 3, I have what I had in the previous diagram plus 2 more. And in diagram 4, I had what I had in diagram 3 plus 2 more. Now, I'm thinking that way just because I'm looking for a pattern. So I can see that every time I go from diagram to diagram, I'm going up by 2 sides. That might be helpful later. Alright, so if I want to know the number of sides in 6 polygons or 10 polygons, I could just simply extend my table. Sides going up by 2. And so we have 21 sides in 10 polygons, 13 sides in 6 polygons. So that answers these questions here. Now we're asked to find the number of sides in n polygons. So what does that mean? So that means that if I were to take any number of polygons, let's suppose 100, how many sides would that be? Well, one strategy you could definitely do is you could continue the pattern going downwards like so, all the way to 100, or maybe you can find some faster ways to get there. But it would be more convenient if we could find a pattern not just going downwards, but going across. In other words, is there something I can do to the number in the first column to get the number in the second column? Is there a pattern going from here to here? Now generally at this level, the pattern we're looking for involves some kind of combination of adding, subtracting, multiplying, and dividing. Okay, in higher grades you'll get into more complex patterns. But for now, we're just looking for a simple pattern involving those things. So we trial and error this is basically how we do it. So for example, let me just take something that I know isn't going to work, but just to give you an idea of what you have to try. To go, for example, from 1 to 3, I could say, well, if I add 2, I go from 1 to 3. But if I go to the second line and take 2 and add 2 again, I don't get 5. So that pattern isn't working. Alright, so is there something else I can try? Well, we talked earlier about the fact that the numbers in the second column are going up by 2. So I need to do something to cause the numbers to go up by 2 each time. Okay? And if you think about multiplication, 2 times 1, 2 times 2, 2 times 3, that causes the numbers to go up by 2. So the reason I bring that up is that that's a good indication that there's a multiplication of 2 involved in this pattern. Alright? So let's try that. If I multiply this by 2, 1 times 2 is 2. Do I get the number in the next column? No, I get 3. But if I added 1, I would get 3. All right. So let's try this pattern on the next level. If I had 2 sides and I multiplied that by 2 and added 1, would I get 5? Yes, I would. With 3, if I multiplied the 3 by 2, which is 6, and added 1, I'm getting 7. I've found a pattern that's working. Everything is consistent in my pattern. The changeable thing is my n. So if I come down here to 10, let's just try it out. That should be 2 times 10, which is 20, add 1. Sure enough, that gives me 21. If I have 100, that'd be 2 times 100 plus 1, which would be 201. Okay? So if I have n sides, okay, and here we come to the generalizing, representing our number of sides with a pattern, with algebra, it would be 2 times n, which we can write as 2n, plus 1. And that's our expression for the number of sides. If I have n polygons, it will have 2n plus 1 sides. And we can, if we want, put this together in an equation. What we're saying is that the number of sides, s, is equal to 2n plus 1. And like I say, if I now want to know the number of sides with 100, I can pop 100 into that position and work it out. I have generalized my pattern with algebra. The number of sides, we're saying, can be found by doubling the number of polygons and adding 1 each time. Okay? Here's the pattern in words. Here's the pattern in a table. And here's the pattern using algebra. You'll see how nice and concise it is. Let's just look at another set of numbers and see if we can generalize the pattern. We have our independent and dependent variables, and we have a set of numbers. The independent variable is going up by 1, while the dependent variable is going down by 3. Okay, and remember, the down by 3 is an indication that there's probably a multiplication of negative 3 involved. My pattern is represented as a table. I could represent my pattern on a graph if I wanted to. If I just quickly plot these points, you'll notice that when I do that, they line up in a straight line. So we have our relationship in terms of a table, our relationship in terms of a graph. Now, when your graph of your relation is linear, everything lines up, that's an indication that the pattern you're looking for is going to involve multiplication, division, addition, and subtraction only. Nothing more complicated than that. So let's try to find the pattern going across. If I take negative 2, and we've already talked about, we think this pattern will involve multiplication of negative 3. If I take negative 2 and multiply by negative 3, I get 6, but I need to get 7, so if I add 1, that will make this work here. Will that same thing happen here? If I take negative 1 and multiply by negative 3 and add 1, does that give me 4? Yes, it does. If I take 0 and multiply by negative 3 and add 1, do I get 1? Yes, I do. So I can see that the pattern seems to be take my x value, multiply it by negative 3, and add 1. So in my table, if my independent variable is x, then my dependent variable is found by taking negative 3 times x and adding 1. There's my expression for y. And if I want to make an equation out of that, I can say that y is found by taking my x, multiplying by 3, and adding 1. What I just said is one way to represent the relation. Here's the algebraic way to represent the relation, along with a graph and a table. Multiple ways to represent your pattern.